Sweet. Rolling right along. Hi, I'm Evan from Virginia in the United States, and I'm going to talk a little bit about some of the work we've been doing to look to see if we can use mechanical work to predict similar trends as metabolic measures to measure the energetic cost of walking. And we're doing it in humans, and I've realized that's important for this group. And so currently, when we measure this in humans, the two most common ways to do this are to use something called indirect calorimetry, and this requires that the activity can be performed continuously by the participant that you're trying to measure. And then on the other end, we have muscle energy expenditure models, and these do depend on highly specific parameters for the muscles throughout the body and any pathology that these people have. So these limitations become even more apparent when we start looking at people with pathologic gait or people that use assistive devices to get around. And so given these limitations, yet areas for potential application, there's a question open to determine if we could calculate this energetic cost from more mechanical as opposed to these physiologically based methods. And so, as we know, we as humans use muscles to generate our motion, right? And so each muscle is producing force as it changes length. So we could say that each muscle is doing work. And we also know that muscles can only pull, so we have these antagonistic muscles acting to control the motion at each joint. If we consider this from the joint level, then we get a resultant moment at each joint, and consequently work is done on each joint by the muscles. And so it has been assumed that the joint work represents the work done by all of these muscles, but for mechanical work to really be a reasonable metric for energetic cost, we need to demonstrate that we get similar trends when we use these mechanical methods for energetic cost as we would get for those indirect calorimetry methods, which have been used as the standard. So this brings us to our main question that we set to answer today, which was, does joint work produce known trends between energetic metrics and walking speed? And so repeatedly in the literature, they found this U-shaped relationship with a minimum near your preferred walking speed, where we increase in energetics according to VO2, energy, and metabolic power. So can we use another metric to also get this similar trend? And so to do this, we brought in 19 participants into our motion lab, and we had them walk at 6 different speeds relative to their own preferred walking speed, while we simultaneously collected the input for mechanical and metabolic energetics metrics. And so what we get from this is this is a big plot. We have the hip, the knee, and the ankle. And so out of our inverse dynamics calculations, we'll get joint angles and joint moments. We can calculate the change in that angle and multiply it by the joint moment to get what we're calling joint work in this situation. And so when we look at this joint work, though, we notice that we get both positive and negative contributions to joint work. And we know that both positive and negative contributions cost chemical energy for your muscles to produce. And so we would take this as the absolute value to start, and then sum all of the joints that we're using in the model to get total work through the lower body, which is plotted on the left with all the contributions in color and the total work in black. And so the area under this curve will give you the single value for mechanical work in the gait cycle. However, we also know that there's different energetic costs to doing this positive and negative work, so it wouldn't be straight just take the full contribution of that. So we wanted to look at how weighting these would change our relationship to the energetic cost from the metabolic measures. And so we scaled these across a large range so that we could try and force a difference. However, when we actually did this, we found there's a strong correlation for all the weighting conditions, and this correlation strength was reasonably invariant to the weightings that we applied, all the way from only negative contribution all the way up to only positive contribution. And shown here on your right, my left, would be the correlation plot for that when we use equal weightings, which is right in the middle of the things that we tested. And so if we try to get an idea of what this actually looked like, because we were trying to predict the trend, we can see the trend from the metabolic cost on the left in black, from mechanical cost in green on the right. We do have a little bit higher variance from the mechanical metric than the metabolic cost. And then if we look at what these weighting schemes, because while they were very close, they weren't exactly equal, we plot those all on top of each other. So now we're doing difference from the minimum, so just how does energy increase from your preferred speed, with the metabolic cost plotted in black and the mechanical costs weighted to different schemes plotted in colors. We do see that we're reasonably predicting this trend, right? It goes up when it should, it goes down when it should. However, when we get towards the slower speeds, it's going to be really important to include this negative work contribution more so than it might be at faster speeds, which was interesting to find out. So ultimately, we think that you can use this mechanical stride work when you include both positive and negative work to predict the metabolic trend for cost of walking. And this is really useful because now we can calculate this cost for a single gate cycle. And this will enable us to calculate the energetics during activities and in pathologic populations that previously you wouldn't do continuously, where people wouldn't be able to walk for as long as we would need them to. This also requires exponentially fewer parameters than would be needed for the computational muscle models. And it's also not reliant on the assumptions that we have to make in order to solve the muscle redundancy problems. So thank you so much for your attention. Happy to answer these questions.
So did you look at any other activities? It's like, I think what you're getting at is that there should be this inherent physiological relation between work. Does it work if you don't walk? Like if you go upstairs or jump, rock climb?
So there was one out on rock climbing. There's no they didn't have VO2 on at the same time, so we don't know. They got about 10 times higher than usual, but you are going up, and possibly Jonathan would know because he did the climbing robots. We think that might be the cost of gravity because it's just about 10. Right? We are currently doing, if you walk with a posterior walker and you drag it around with you, that should increase your energetic cost. And so for people that don't usually need to use walkers, it makes it a lot harder. For people that use them regularly, walking with them actually helps their stability so much that it decreases their cost of walking. And so we're starting to look at some of that for validation as we have as well. Yeah.
So for both the gold standard of metabolic cost and your mechanical cost, in both of them we're fitting a model to the data set. What's the comparable fit of your stuff to what's the gold standard? They both look rather variable to me.
Oh, like the fit of the data, data points to the model?
Yeah, U, but how good is the U in either case?
Yeah, so in either case, so the VO2 data is like 0.55-ish is good. I believe there's somebody out of Gillette's in Minnesota that has done a different way to pull the best. Basically, this is the noisiest measurement that we can collect, as I understand it, is this breath by breath. Our fit to the mechanical is a little bit worse. It's about 0.4. Technically, that's still a reasonable correlation, but it is not quite as good as the VO2.
Okay.
Yeah. Yes, sir.
You didn't distinguish between, you have a joint power, and you have muscle power, and then you have muscle metabolic power. And your final comparison was between joint power and metabolic power. And you didn't say where the error, you said that you described it, whether that had to do with the transition from muscle power to joint power, or whether that had to do with the transition from power to metabolic cost by the muscle energy use not being mechanical work. You understand the question?
I understood the first half, and then I got lost.
I'm just giving your introduction. You started with muscle power,
Mm-hmm.
and then you said we were interested in metabolic power.
Yes.
So then we have this approximation of muscle power, which is joint power, and then you compared joint power to metabolic power, and you have some difference. Is that difference more because the metabolic cost of muscle is not work, or is it more because the muscle work and joint work don't match?
Part of it is the muscle work and joint work don't match as well. There's a lot of, in the soft tissue, there's reabsorption of power there is one of the things that we think it's due to. And then there are different ways that you can go from that breath by breath measurement to what you get from metabolic power. And I looked at 3 different ones, and you can significantly change both the spread that you get to the quadratic that you fit to it, as well as where that quadratic tilts as you go through. And so I used energy expenditure, one of the Brockway calculations, because that gave us the tightest fit to the quadratic. So that seemed like the best thing to try and target. We'd be happy to talk more later, for sure. Yeah.
So maybe I did not understand everything correctly, but it sounded like the relative weights of positive and negative work don't matter.
Yeah.
Which probably means that in your data set, the ratio of positive and negative work is constant across the parameters.
Yeah. So they're almost constant. They're less constant at slower speeds and higher speeds, which was interesting to find out. And then the ratio, which was the ratio of negative to positive work. What was more interesting to us that I didn't present here is the ratio between in-plane, so sagittal plane work, and out-of-plane work changes. Out-of-plane work becomes a much larger contribution at slower speeds.
But you don't have data on slopes,
On slopes?
where negative and positive work contribution would vary.
No.
Okay.